So we have now Gerhard Knieper for his third lecture on his Minicourse. Okay, Gerhard.
Okay. Yeah, welcome to my third lecture. So before I really start, let me remind you what we did so far. So there were a standing assumption on the manifold which we consider. So we have closed Riemannian manifold without conjugate points. And that means that we can represent it as X, which is a universal cover, which is diffeomorphic to Rn in this case, and is a dimension of M, and mod out a discrete group of isometries. And if we leave it like that, we cannot say much about the dynamics, say, of the geodesic flow or whatsoever. So we need to have at least some conditions, which are kind of, I call it coarse hyperbolicity conditions. And one is that this manifold, which we consider, should admit a background structure, which is a metric, another Riemannian metric, which has strictly negative curvature. So that's one important, maybe the most important feature. So maybe you can even weaken this a little bit by assuming something like Gromov hyperbolicity, but I don't want to do that. So I really want to have a second real metric. And then comes another, the second condition, which might, I'm not sure if one really needs this, but for convenience, we introduced the second condition, which means that if you look at the geodesics, so if I lift the metric to the universal cover, I can also talk about geodesics there. And you look at two geodesic rays initiating from a common point, and if they are not the same, then they diverge. So that is the second condition. And these conditions are kind of natural. For instance, if you have a surface, closed surface of genus at least 2, both conditions are satisfied. So by uniformization, you have this background metric of negative curvature, and the second property is H2. It was already proved by, I think, by Hopf or whatever. I mean, this is an old result. And this is my standing assumption on the manifold which we consider, and we are interested in the geodesic flow. I was explaining that at my first lecture, so we were interested in measures of maximal entropy, maybe uniqueness of measure of maximal entropy under some condition, and the other thing is somehow as an application we want to somehow getting good asymptotics, maybe even in the sense of Margulis on the growth rate of periodic orbits. Okay, now under this assumption that we introduced a measure which is well known, which is a Patterson-Sullivan measure. This exists under this condition, and the Patterson-Sullivan measure is actually not a measure, it's a family of measures on the boundary. And there's 3 important properties. One is this gamma equivariance. So if you take such a measure and you move the point P by the group gamma P, then you have this kind of equivariance property that gamma P of gamma A is the same as mu of, oh, I didn't want to do that, mu of P of A. Okay, so that follows more or less by the construction of this measure. And the other one is that any pair of measures are absolutely continuous, and you can write down precisely the Radon-Nikodym derivative. So it's if you choose Q and P and you look at the Radon-Nikodym derivative with respect to this point psi is a point at infinity, then the Radon-Nikodym derivative is given by e to the minus h, and then comes this Busemann function based at xi. So I introduced this Busemann function last time. It's kind of the levels of this Boseman functions are horospheres, and so if you think of this function here, it has two variables q, and p should denote the level 0 of. So if you have a horosphere passing through p, then if q is on the same horosphere, then the function is 0. So that's the Boseman function is a kind of assigned distance function. And the second, the third property is that this, under this condition, that's not always the case, but under this condition, the support of the measure is everything. So you have a full support of this measure. And now we also proved last time the famous shattering lemma, which is well known in negative curvature. So I repeat what the shattering lemma is saying. There are some slight differences to what you have in usually in negative curvature. So you have to fix. So there exists a constant which is universal and depends on the two metrics which you have: the background structure and the metric G. You cannot say much about the constant, but this is a priori given. And another constant B, which shows up in this inequality. Then if you look, if you measure somehow the shadow, so let's say for the shadowing lemma, the shadow of the ball of radius rho about this point x. So I have this here, this ball. And now psi is a point at infinity, and somehow you send out light beams kind of back to infinity, and then you see this black region, which is this kind of shadow which you produce by using these light beams from psi. And now if P is a point on the ray, so there exists a ray joining this point at infinity to this point x, then the measure, the Petersen-Sullivan measure of this shadow is proportional to e to the minus h distance of the point P to the point x. So in other words, if P moves away, then this exponentially from x towards psi, then this measure exponentially decays. So in a very uniform way. So that's what the shattering lemma is saying. And I also should mention that rho you need to require some conditions on rho, because it might be that if the radius of this ball, so this ball is too small, that the shadow is just one point. So that happens if the geodesics stay so this family of geodesics stay in a small neighborhood, and then you get just a point, and then it's certainly not true. But the rho can somehow be chosen such that the shadow in the boundary will contain an open set. And since the measure is positive on open sets, at least you get something, and the estimate tells you exactly what you get. So that's important shadowing lemma. Okay, so what are we doing with this measure? We are interested in a geodesic flow, so you want to get invariant measures for the geodesic flow. And therefore, the idea is now to use a product measure, but not quite a product measure. It's almost a product measure. It has to be weighted with some function. And this is this lemma, which I also explained last time. I'll try to explain this last time. So using this Petersen-Sullivan measure, you produce another measure on the boundary, on the square of the boundary, which uses a fixed point P, so reference point P, And then this measure is a product measure up to this function here. So this is important. It would be not important. You get also a measure if you don't use it, but in order to get a measure which is somehow invariant under the gamma action, you need to have this additional term here. And what is this term? In the exponent is a well-known function, which is usually called the Gromov product. So it depends on 3 points. One point is the point P, which we choose, and the other points are at infinity. So it can be written, or at least explained geometrically in very easy terms. So how do you, what is the geometric meaning of this Gromov product? So you fix to this point, associate to this point psi and eta, there are two Horus spheres which are based at these points and contain this point P. That are the green circles which I draw here, that are the Horus spheres. And now you pick a geodesic joining psi and eta, and then the Gromov product is nothing else than the length of the arc which is cut out by these two Horus spheres. So that's a Gromov product. You have to check that. Of course, I said maybe the connection is not unique, but it turns out that if you take another connection, you get another geodesic, this arc will have the same length. So that's what one has to check by using Busemann functions. Okay, so that is now a measure which is invariant under the gamma action. Okay, one has to prove this, of course. I did not quite do it, but it's a kind of easy. It's easy to do because it relies on this transformation rules of the Peterson-Sullivan measure, and then which involves Busemann functions, and the Gromov product can also be written in terms of Busemann functions. So it's basically an easy calculation that this is really a gamma invariant difference, a measure which is gamma invariant under the action on the boundary of the squared boundary of the ideal boundary. So. Okay, anyway, so that's the first thing. And now we are almost done to get an invariant measure for the geodesic flow by introducing, so that's now something new. I didn't explain that so far. So you define a map, which is kind of the endpoint on the unit tension bundle of the universal covering, which associates to each vector the endpoint of the geodesic corresponding to this vector. So that's written here. So I take a vector v in the unit tension bundle, and I denote by v minus and v plus the negative endpoint and the positive endpoint of the associated geodesic with initial direction v. Okay. So that's one thing. And now let me just assume to explain the construction, how one goes about, how one does it in case of negative curvature. So negative curvature is quite easy because the inverse of a pair of different points at infinity will give rise to a single trajectory of the geodesic flow. It's exactly one geodesic. So there's only one geodesic joining any 2 points, and the way it's defined, it's not the geodesic on X, it's a lift to the unit tension bundles or the geodesic trajectory of the geodesic flow. And now having this geodesic, you use a Lebesgue measure on this geodesic, and you simply define a measure by integrating this, by looking at this following integral. You have this measure on the boundary squared, and then you take the connecting geodesic, you intersect it with the ZA, you take the Lebesgue measure, and this gives you a measure on of any Borel Z in the unit tangent bundle of the universal covering. So, okay. So this obviously, this mu bar was gamma equivariant. This mu tilde measure is now invariant by definition, basically because it takes a Lebesgue measure by the geodesic flow, and also gamma invariant. Therefore, it will descend to a flow invariant measure on the unit tangent bundle downstairs. And I'd like to get a probability measure, so you should normalize it, and this normalization I call mu. So this is now an invariant measure on the unit tangent bundle of my manifold M downstairs. So this would be okay in a negative curvature, but we are not in negative curvature. So in particular, we do not have a unique connection of points at infinity. And there comes a technical point, but can be solved in a very abstract way. It's possible, that's which I don't, that's some abstract theory. It's possible to select for each pair of points at infinity a geodesic, a connecting geodesic in a measurable and gamma equivariant way. You have to check this. This point we had to overcome, but it's possible to do that. And once you have done the selection, you can basically construct the measure in the same way as a negative curvature. So you have to believe me that this is possible. It's a kind of an abstract argument, but it's possible to do this.
But the selection is not unique in general?
No. You can have many selections. And then a priori you would have different measures, but at the end you want to show that you only get one measure. A priori, the selection is, I don't know, maybe in dimension 2 you could say I take the geodesic with most left or something like that. So maybe there's some more natural choices, but in higher dimension there's no way. I mean, don't know how to select it. There is some, so of course I did more or less this kind of things in the case of non-positive curvature. And non-positive curvature is a little bit better because if you look at all geodesics connecting 2 points in infinity, they will bound a flat strip. And what I did in non-positive curvature, not to take the length, the Lebesgue measure on a geodesic, but takes the volume of this flat strip. And that is also worked, but it's because you have this flat strip theorem, which you don't have here in the case of no conjugate point. So I have no idea. It could be a complicated structure of geodesics, which are joining such a pair of points at infinity. So it's not so clear what to expect. Okay, especially not in higher dimension. Dimension 2, it's maybe you can say something, but in higher dimensions, it's certainly hopeless to say much about this set. Okay, so let's assume we constructed such a measure. Whatever selection we did, we only use abstractly the properties of this measure, which we somehow use and showed so far. This is what we have. And now there comes a third point. I said at the beginning, we are interested in measures of maximal entropy. So question, is that a measure of maximal entropy? Therefore, we have to compute the entropy of this measure. And that is done in a more or less standard way. First, I introduce a convenient metric, which is kind of a geometric way of defining a distance on the unit tension bundle, either of x or m. This is exactly the same, by saying I call this distance d1 because it's defined like that. You take two vectors and you take the geodesic for time 1 between 0 and 1, and you look at the maximal distance of the geodesic at time t of the possible distances. So, and this is definitely defines a metric on the unit tension bundle. Okay, so this is what we use. And now, in order to compute the metric entropy of this measure, we introduce, as usual, a measurable partition of the unit tension bundle on the quotient. Later on, we lift this, but first of all, we have to do on the quotient. And we assume that the diameter of the sets in this partition is small with respect to this metric, smaller than epsilon, and then we do what one always does. One iterates this partition under the time 1 map of the flow. So I think since we are here, all are experts on this kind of stuff, I guess. So I have this usual standard notation. So you look at the nth iterate of this partition A under the geodesic flow. And then you get a new refined partition. And if you have an element of this refined partition, then you get that such an element, such a set, in this refined partition is alpha is in the intersection of balls of radius epsilon around this orbit point phi kv, and you pull it back with a geodesic flow back and takes the intersection of this. And in a more geometric way of understanding what this is, it's a set of unit tension vectors such that the unit tension vector W and the associated geodesic stays within epsilon for the time interval from 0 to n. So you take all vectors W such that the distance is smaller than epsilon. So that's what you get. Okay, so that's the partition which we are, and then we want to somehow compute the entropy of this partition. And since our measure is actually really only clearly understandable on the universal cover, you have to somehow compute the entropy of this measure using the universal covering. And now I do the following. So epsilon, of course, can make it arbitrarily small, and make it as small as that is smaller than the injectivity radius of the manifold. So I hope injectivity radius is known. So it's a kind of the injectivity radius measures in which ball the exponential map stays injective. So it's not so important to really understand it, but what we can do with this. So I assume epsilon is smaller than the injectivity radius, and if this is the case, then the measure of each of the elements alpha in this refined partition is smaller than some constant times e to the minus hn. So it decays exponentially, and then I guess somebody who knows about entropy knows that this means, and we will show this, but it means that the entropy of this measure is equal to h. And h is a topological entropy, then it would have, the measure would have maximal entropy. So how do you use the fact that epsilon is smaller than the injectivity radius? So you lift everything to the universal cover. So let me choose this point P, which was used in the definition of the measure mu. That was this kind of reference point. And we lift now the partition alpha, or this element of the partition, this alpha, this set alpha, to a set alpha tilde on the universal covering, such that the first thing is trivial, that the projection of any vector in this lifted partition has a distance smaller than the R0, which is the diameter of M. That's just because you have this fundamental domain, and the fundamental domain has the diameter of the fundamental domain is basically the diameter of the manifold, and you can have this. And the second thing is where you use the injectivity radius. So if the geodesics downstairs stay close, small, and a distance smaller than the injectivity radius, you actually can lift all the geodesics in this partition to geodesics which also stay in the universal covering in a distance smaller than epsilon. So this uses certainly, because if you go beyond the injectivity radius, cannot do this, and they might somehow the distance might not be controlled. But as long as the geodesics downstairs are in a neighborhood, stay in a neighborhood which is always smaller than the injectivity radius, you can do that. And this way, and you have this for all elements V and W in this lifted partition alpha tilde. Okay, so that's now, we are now computing the measure of alpha tilde with respect to the measure which we just introduced. So, but the measure which introduced involves somehow boundaries at infinity and endpoints of geodesics. So I have to do this. And yeah, I draw a little picture. So I choose now a vector in this lifted partition, any, doesn't matter. And this is this red curve here, or the red vector, and I take the curve till time n. So then I get another point x. Okay. So now I take any other point in the partition, and by definition, the other point will correspond to a vector such that the geodesic stays in epsilon neighborhood for this time window 0n. In particular, the geodesic CWN has distance smaller than epsilon from this point x. So x was the endpoint of this fixed geodesics in the partition which we choose. And now you do the following. You look at the endpoints of this vector v, or better to say of this corresponding geodesic. And you get the minus infinity, so you get the past of this vector. So this is CW of minus infinity. And what you get is that the infinite, the geodesic in the other direction, and this endpoints, V plus, is by definition in the shadow of the ball bx epsilon when you shadow from this point w minus. Yeah, that's by definition, because the geodesic will hit this ball, and this will certainly be in the shadow of this ball if you do the shadow with respect to this point w minus. So that's important. More or less trivial translation of what we have, and now I take the full partition, no, not the full partition, this part alpha tilde, this element of this partition, and take all endpoints of this. So you get W minus W plus. And what I just said is that this picture here tells you that the endpoints of this Z alpha tilde is contained in a union of which is here in this union. So you take W minus is the minus endpoint of this vector V, so you go backwards, and you take a cross product with shadow from W minus from light beams initiating from coming from W minus of this ball Bx epsilon. So that's where the set is contained. And this is this kind of description is useful to compute now the measure. Namely, you have now two factors, the first factor and the second factor. The second factors are always kind of projection of balls, of the same ball actually, but the point where you shatter from will change. But nevertheless, the first thing is that you get that the Peterson-Sullivan measure of this projected Z, whatever W you take, is smaller than a constant times e to the minus hn. And this, I will explain this, is a consequence of the shattering lemma. And how is this a consequence of the shattering lemma? Now you have the following situation. So maybe I draw here again another one. So you have you can choose another geodesic coming from having this point x v minus as a negative limit point and connects this to x. Oops, x. Now I take a point q on this black line, which has also exactly distance n from x. So this distance should be n. So that's what I've written here. You take a point which is uniquely determined on this ray connecting w minus and x, such that the distance of q and x is equal to n. So this point q is certainly by basically construction and using Morse lemma and things like that, is in a bounded distance from this reference point P, because P is where the measure which I actually use, mu P. Okay, and having this, that P is from in a bounded distance, bounded by a universal constant, depending on the two metrics, you get that the measure of mu P of this projected Z can be estimated. I know I change the reference point. I go from P to Q is e to the h dpq. That comes from the Radon-Nikodym derivative, because the Busemann function always can be somehow bounded by the distance function. So this is this kind of Radon-Nikodym derivative times the measure now measured at point Q of the point Q of exactly the same Z. So that's what you do. Now you have here Q and X. But now I'm basically in the setting of the shattering lemma, because I have a geodesic ray connecting V minus, W minus and X. And for this kind of situation, if I have a point in between, I can use the shattering lemma. So the shattering lemma tells you that the measure mu at point Q with respect to Q of this ball is smaller, so I only use the upper estimate than this constant times the distance of Q to X. So I choose this to be n, so it's e to the minus hn, what you get. So that now this means the second factor is always exponentially small with always the same exponential bound. So you have this, you have a good estimate on this here. And now I claim that this is already enough for getting at least, not maybe at the beginning, not maybe for the measure, just for the measure which on the boundary point, so on d squared x. So I claim now that the measure mu bar, which was introduced above, so here this measure, where was it? This here, this measure which was used to get this invariant measure, that this measure is now of the endpoints of this alpha tilde as a right inequality. Okay, that this inequality holds. Why is this? You actually need only to estimate the first, the second term in this product, because the measure mu p is finite. So whatever this is in the first set somehow will be only a constant, and also this measure also involves this factor which comes from the Gromov product, but the Gromov product on this kind of points, endpoints which we are considering, is also bounded from above. So we have also a universal bound for this Gromov product. It's not bounded in general, but if W minus and W plus are really not very close to each other, it stays bounded. And this is, of course, the case. You get that this estimate for the measure mu bar, and to get the measure mu, you only have to check how long geodesics span in this set, and this is by definition also bounded, and therefore mu alpha, the projected alpha, will also have exponential decay of the measure. So mu alpha is more or less than a constant times e to the minus hn. So that's basically then follows from the definition of this measure. So what you have, that this partition somehow, the iterated partition, exponentially decays. And now, yeah, so far clear? If they're not clear, then
So may I ask you a question? As you
yes, sure.
So comparing with this, with the negative curvature, so here you are constructing your measure of maximal entropy, going to the boundary, in fact, and then using Hopf parameters. So there is something that you gain when you do this game. The measure is locally a product measure, and here I don't know what. It is important because product measure uses to prove Bernoullicity and many things. So here, do you have?
Here I'm not using any special features. Of course, if I estimate the measure, I just use this kind of product construction. Yeah, I use this, but so far I did not use any other properties of this measure.
Let me be more precise. So here you don't have this stable, unstable manifold on the like the hyperbolic.
Yeah, you have it in somehow. Of course, you have. I mean, you have candidates of the stable and unstable.
Exactly.
They are not really transversal. That's the whole. Somehow you have stable and unstable manifolds, but they are in a very coarse sense stable and unstable manifolds. So you are not. Then nothing is converging, and you don't know. I mean, a priori, of course, if you pick such an orbit which connects 2 points at infinity, and you assume that the Lyapunov exponents are on 0.
Yes.
Then, of course, you get some, that would correspond to some transversality of these two Hall spheres. But in this case, even, I mean, this is really things which are completely unknown. I have no idea, even if you take a surface of higher genus, and whether the metric entropy of this of the standard measure, the legal measure, would be positive. That means it could be that the Lyapunov exponents, I mean, it's probably not true, but it could be that the Lyapunov exponents with respect to the legal measure are almost everywhere zero. And that means you have no transfers. That is a difficult situation. So you have to work with Lyapunov exponent. You can do that, but you don't know much about this. That's the problem with this. So transversality doesn't hold, at least you don't know, and you have it in a coarse sense. Of course, if you look at all geodesics connecting 2 points, they stay in a bounded distance. So you cannot have a complete. You cannot have that the horospheres completely coincide with respect to different directions. That's not possible, but I have no idea about transversality and things like that. And you should, depends how you define. If you define stable manifolds as usual, then you're not getting very much.
Thank you.
But nevertheless, I think somehow a replacement of the of this stable manifolds are exactly the boundary structure. This is kind of you see it at infinity, and this is somehow a replacement of this what you usually have if you are in a uniform hyperbolic situation where you have stable and transversality of stable and unstable manifold. Yeah, that's yeah. Okay, so and the corollary from that is kind of standard, and it's as usual. One computes entropy, takes the entropy of this partition, and then you plugging in this decay of the elements of the partition, you get that the entropy of this measure is bigger than the topological. So this is the same as, of course, the same as topological entropy. This is my H. Okay, and that means this measure has maximal entropy. So whenever you have this kind of assumption, which I made at the beginning, you get a measure of maximal entropy. And also what I didn't say is that the measure has full support. This follows from the fact that the Petersen-Sullivan measure had full support on the boundary. So it's a fully supported measure of maximal entropy. Okay, but then of course the question is, can you have other measures? And that's what we want to actually to show, that at least under certain conditions, the measure should be unique. And yeah, that's the fourth part, I think, of this lecture. So it's about the question, is this measure of maximal entropy unique? And okay, let me look again at this general situation. So you have a closed manifold without conjugate points, and this conditions H1, H2, which we introduced. And under this condition, we just mentioned it, there are two naturally defined invariant sets. So one set we call the expansive set. So expansive set is somehow kind of the same thing as transversality of stable and unstable, but not quite transversality. Maybe it's a topological transversality of stable and unstable manifolds, in the sense that it consists of all vectors in the unit tension bundle, such that the lift of the geodesic, the lift of this geodesic CV or downstairs to the universal cover, will produce a geodesic which uniquely connects its endpoints. So that is basically this picture here. So, and this is what we call expansive set. Okay, and then of course naturally you have, and this is by definition basically a set which is invariant under the geodesic flow. some set, and you can have also the non-expensive set. That's a complement of this. And the problem is there could be the non-expensive set could a priori also carry a second measure of maximal entropy a priori. I don't know. I mean, it's probably not the case, but I have no example. But in principle, it could happen. And to exclude this, the second property, the second case that there could be a measure concentrated on the non-expansive set of maximal entropy, we introduce the notion of entropy gap for the set. What does it mean? So it's a kind of a topological entropy, but in terms of using the variational principle in some sense. So we say that our manifold, the manifold which we introduce with these two properties, fulfills the entropy gap if the supremum of all entropies where you take measures, so this should stand for invariant measures of the geodesic flow. Probably it's enough to take ergodic, but I didn't mention that. We take all, this is the set of measures under the geodesic, invariant measures of the geodesic flow, and you take only measures which have their support on this non-expansive set. So which have such that the measure n, the non-expansive set has full measure. And I want to have that this set should that the supremum of all these entropies should be smaller than the full topological entropy. So that's a condition, and we call this entropy gap, so that this set should not can carry entropy, but not as much as the topological entropy. Okay, now in non-positive curvature, I had this paper many years ago from '89. This was the result in this paper. The main result of this paper was the uniqueness of the measurement of maximum entropy for non-positively curved manifolds, which have an extra condition, which is a rank 1 condition. Now, I want to explain this. Typical metric of non-positive curvature is a rank 1 metric, so there's some rigidity. If it's not rank 1 and it's not a product, then basically you are in a symmetric space case. So basically all metrics with non-positive curvature are of rank 1, especially if you are on a surface of higher genus, you can, if non-positively curved, then it's automatically rank 1 metric. And in this paper, actually, I proved the uniqueness of the measure of maximal entropy without using this gap. So I did not use this gap. So I just proved it with some geometric methods. I proved that the measure is unique, and I deduced from that the entropy gap, because you cannot have, if it's unique, you cannot have another measure staying in the non-expansive set and have the same topological entropy. So that's one can deduce from that this entropy gap. And 2 years ago, I think Burns, Alemanha and Thompson, I'm not sure, they had another way of reproving my theorem by somehow showing that this entropy gap in non-positive curvature exists. So that was a different way.
We are running out of time to let you know.
We're running out of time. Okay. Good. Then, yeah. So that's what we, that's what we want to do. And next time, or the last lecture, I will use to show that if the entropy gap is fulfilled, then actually the measure which you introduced is a unique measure of maximal entropy. And the proof is slightly different than what I did in my paper from 1908 because this paper uses convexity of metric, and maybe it's possible also to do this method, but this is not so clear. And instead we use an approach which is much closer to the original idea of Bowen, using specification, but not the way Bowen did it, but in a more general way, which was somehow introduced by Alemanha and Thomson, this kind of coarse specification. And we show that this coarse specification is somehow, in our case, can be checked that this is true. And then we prove using this that the measure of maximal entropy is unique. Okay, that we will do tomorrow. And yeah, okay, thank you very much.
Okay, thanks a lot, Gerhard. Thanks. So there are more questions. Katrin, you want to?
I think in the paper you mentioned with Burns, Alemanha, Fischer, and Thomson, they have a priori they have a gap by some other thermodynamic property. So they assume the gap and construct the or show the uniqueness of the equilibrium states, not just entropy. So,
but they also proved the existence of the gap without using my result. At least that's what I have heard. Yeah,
yes, yes. They in the concrete case of non-positive curvature, they showed the gap.
They showed the gap, and then they used this specification arguments to get the uniqueness.
Oh, okay, so I missed this point.
That's
it's a very nice paper. Yeah,
yeah. That's slightly different from. So in my case, it was kind of consequent, but they show that the gap exists, and then they use this method to prove it. They get a little more than just a measure of maximal entropy.
Of course,
uniqueness of some equilibrium states with other certain properties, which I forgot exactly the properties are. There are some properties, not the full statement, not for all equilibrium, not the uniqueness for all equilibrium states.
Are you going to talk about Bernoulli or other properties of the measure tomorrow?
Probably not. No, that's not. That's just one lecture left. So I have to explain how to get the uniqueness. So,
okay, thank you.
I also miss. Unfortunately, I want also to talk about closed geodesic and how to get this Margulis estimate and under this assumption. But that's probably. That is the idea is similar than what Margulis did, but as we said at the beginning, the problem is a lack of transversality of stable and unstable manifolds. You cannot work with this kind of Margulis boxes, which are small flow boxes formed by stable and unstable manifolds. And instead of, you have to replace it by some other structure, and the structure is coming from the boundary at infinity. And then one can use the ideas of Margulis, but you need, of course, to use not just acousticity, you need definitely mixing properties of this measure. So you have to have it, otherwise you cannot get this. If you don't use it, you get also estimates on periodic orbits, and this is actually even true in a much more general setting of Gromov hyperbolic metric spaces that we proved many years ago with Corner. It's more kind of an abstract thing, so it works for all Gromov hyperbolic spaces. Or better to say, for Gromov groups, which hyperbolic groups which act co-compactly on groups which act co-compactly on a Gromov hyperbolic space, and then you get also some good estimates for closed geodesics, for the growth rate of closed geodesics, but not as precisely as Margulis did. And for that, you need there's no way to get around mixing, so you need mixing for that. That's clearly the case. And the mixing, of course, nowadays probably different, several proofs of that. The original proof in this setting is due to Babylot. So she proved that once you have agodicity, that you also get mixing. But I've heard that Yuri, you have a different proof, or at least that's for the mixing.
Yes, we actually go directly to Bernoulli or Bernoulli times
You move
rotation.
directly to Bernoulli. Yeah, you move directly.
Under what hypothesis?
We assume non-uniform hyperbolicity.
So this case would apply. Huh? Our case would apply to.
Yeah.
Okay.
For surfaces.
Actually, the result with Maurício and Emerson is in n-dimensional.
Okay. The one talk you presented, no Malka?
Yes.
Ah, no, sorry. Yes. Well,
no. Malka, it was about the billiards.
Yeah,
sorry, about the decay of correlation.
yes.
Yeah.
But this is not written yet, or is it somewhere published?
The Bernoulli property.
Archive? Yeah.
Archive.
It's on archive.
It's on archive. Okay.
Yeah. But I don't recall how. I think we assume non-positive curvature. So we get exactly this. Yeah, we get the same class of examples in which Dan Thompson and one of his students, Ben Call, worked. And it's based on this Burns, Fisher, Knieper, and Thompson previous paper.
Mm-hmm.
So you are not getting it here in our case. We have it, but because the same argument done, which was provided by Babylot, works also in this case.
So if we know that so we actually get that it's either Bernoulli or Bernoulli times a rotation. So in case you know, for instance, by Babylot that it's mixing, then necessarily it will be Bernoulli. So we can go all the way to Bernoulli.
Thank you. Okay.
With Raphael, I worked on these. We had these factors, topological and also factor flows, which model the geodesic flow, and we had an extension of the result on non-positive curvature to no conjugate points with continuous green bundles, which gives a bit extra structure.
Yeah, but this is not fulfilled, unfortunately.
Yes, I know. Well, you have to do something to continue. That was the way out to go a bit more. And there is a student, Adine, he's listening here. He's a student from Raphael. He was working on some more extensions in this direction. He will defend the thesis and soon. So
okay.
Some more general case to discuss. Yes.
Very good.
Yes. Adine, say hello. Do you have a camera?
Hello. Hello, yeah. It's a good lecture that you give. Very nice paper, yeah. You published with Coarse and Alemanha.
Yeah, thanks.
Are there any more questions? Okay, so let's thank Gerhard again.